Welcome to the lectures on modern digital communication techniques. In the previous lecture, we have presented the phase shift keying or the digital version of angle modulation, and we have represented the signal model, we have calculated the signal energy, we have also given the signal space diagram. So, we will exploit whatever we have discussed in this particular lecture and carry forward some of our discussions which we have left there. So, if we would look at the typical signal space diagram that we have been drawing, so what we could think of is, in this case, clearly the way to send the signal would be you need a simple cosine, a carrier cos 2 pi f c t, you would choose the angles and you would do away with that, or you could simply modify the amplitude to be plus t or minus t and you are done with that. Whereas, if you choose m equals to some higher value, that means if I choose m equals to some higher value as in this particular picture, we see that you have a cosine carrier and a sine carrier, that means the I axis and the quadrature, that is the q axis, right. And if we move there, you have a similar thing, only thing is that you have more values in it, but still they could be represented via representation on the 2-dimensional plane. That means, you would need a cosine carrier and a sine carrier, and with components on these carriers you would be able to send the signal. So, typically during transmission you would generate, you would have a local oscillator, you would generate a cos 2 pi f c t, and you would also generate 90-degree phase shifted sine 2 pi f c t. On this you are going to do, you can think of doing an amplitude modulation with cos 2 pi m minus 1 upon capital M, and on this you can think of doing an amplitude modulation of sine 2 pi m minus 1 upon capital M. So, that means we can think of, there is a pulse amplitude modulation going on here, there is a pulse amplitude modulation going on there on two different carriers which can generate this particular signal space. So, if you choose different values of m, you are going to get these locations, and in the vector form they could be easily represented as in here, right. So, that is one important thing which we should keep in mind. The next important thing which we are supposed to discuss, as we did in PAM, is the Euclidean distance between two signal points, that means the two phases. So, if SM1 and SM2 are the signals, so this would be the norm of SM minus SN. So, if you would do this, you could calculate this as root over E g by 2, because this is common in both of them. All you need to do is to take this form, E g by 2 is common in both of them. So, keep it here and we can continue. So, what you are going to have is cos theta m. So, remember this you could write it as theta m, where theta m is 2 pi to m minus 1 by capital M, right, that is it. So, you have cos theta m because of the first signal and sin theta n because of the first signal, that is this one, first component, second component, minus cos theta n and sin theta n, a norm of that. So, if you continue on this, you could get this as, so we would just like to recall how do you evaluate the norm. So, if you would remember, the norm of this was v dot v half, or square root of I equals to 1 to n v I squared. So, since we have this as a vector, we are going to take the subtraction of the first component and the second component. So, we still have to calculate the norm of E g by 2 times the first component is cos theta m minus cos theta n. This is the first component, and the second component is sin theta m minus sin theta n. So, the norm of this vector, where this is the first component, that is the second component. So, that means going by this, we are left with square root of square of this Eg by 2, and you have this term squared plus this term squared. That means cos theta m minus cos theta n squared plus sin theta m minus sin theta n squared, right, and a square root across the whole. So, if you carry forward this, you are going to get a cos squared theta m, you are going to get a cos squared theta n, and you are going to get minus cos theta m cos theta n, and same with these terms. If you collect the cos squared theta and sin squared theta, you are going to get a 1. If you are going to collect cos squared theta n and sin squared theta n, you are going to get a 1. Then you will be getting a term 2 cos theta m theta n, and you are also going to get minus 2 sin theta m sin theta n. So, here again you have a cos a cos b and a sin b. This would expand to cos of theta m minus theta n, and you are going to get plus cos of theta m plus theta n, and this will also result in cos of theta m minus theta n minus cos of theta m plus theta n. So, these terms are going to cancel out, you are going to be left with these two terms, and this would reduce to the expression. So, there is a 2 over here, there is a 2 additional over here. So, what you will be left with is root over, which will cancel out with this 2 Eg. So, I would urge you to do this particular work by yourself, and square root of 1 minus cos theta m minus theta n. So, that will result in 2 pi upon m, because theta m and theta n are nothing but 2 pi by m minus 1, and the other case it is n minus 1. All the terms cancel out except this m and n. So, you are left with this term. From this you can calculate d mean, the Euclidean distance, the minimum Euclidean distance, which will turn out to be root over E g times 1 minus cos of 2 pi by m. So, that means this is the expression of d mean, and we will be using d mean squared at some point when we will be calculating the error term, and you can compare this with respect to the pulse amplitude modulation. And a small note that for given signal energy, the d mean squared is 1, which determines the error probability, which we will come to see at a later point. You can compare and see which of the pulse amplitude modulation or phase shift keying has a better minimum distance for a given energy of the signals from these expressions. So, till this point we have covered two important modulation techniques, that is the pulse amplitude modulation, where you are selecting an amplitude based on bit sequence. The number of bits you would group together to select an amplitude would depend upon the number of amplitude levels. In the phase shift keying, you are choosing the phase based on the incoming bit sequence, and philosophically they are similar in terms of you choose one of the possible options. In the first case you choose an amplitude, in this case you choose a phase, and we have given the signal space representation, we have given the energy computation, we have given the minimum Euclidean distance between two constellation points, which will again play a crucial role when we do error probability calculations. So, with these two we would like to move forward to the next important modulation technique in the domain of digital communications, which is the phase shift keying, which is the quadrature amplitude modulation. Right. So, when we talk about quadrature amplitude modulation, by now all the terms are known to you. So, by modulation what we mean is already known to you in terms of when you study analog communication, you studied modulation, and what we mean by modulation in the digital communication we have also explained, which consists of two parts, the symbol mapper followed by the up conversion. So, generally up conversion is what you study in the analog communications. Here symbol mapper is a special part which we have described. So, modulation part we have no issues. If we talk about amplitude, we are clear. So, if we talk of amplitude modulation, we already know about it. If it is quadrature, we have introduced the term quadrature in the previous lecture, and in a few minutes back also we have talked about the quadrature. So, quadrature for us would mean the carrier in phase which is in quadrature with each other. That means there is a cosine and there is a sine which are at 90 degrees with each other. So, being at 90 degrees, they do not interfere with each other. So, now when we have quadrature amplitude modulation, although we know the terms individually or in some groups, this when put together has a different meaning altogether. So, this quadrature amplitude modulation is all about modulating the amplitude of quadrature carriers. We have already seen the modulation of amplitudes of quadrature carrier when we studied phase shift keying, and while doing that we have actually discussed the expression where we said that if you look at this expression, you have quadrature carriers which we had identified, and this is the amplitude, that is what we had explained, and in the signal space diagram also we had explained the same. However, we may note that the amplitude is dependent on a single parameter, that is theta m. That means the amplitude of the I component and the in phase and the quadrature phase component. So, if we call cosine as the in phase, then sine is the quadrature phase. They are dependent only on the angle and nothing else, right. Whereas, if we talk about the if we are going to talk about the quadrature amplitude modulation, here we are talking about modulating the amplitudes through independent data streams, which is quite in contrast with what we have studied before. So, we could write the signal representation in various forms, and one of the forms, well, we could change the order of writing, would be the amplitude modulation of the cosine or the in phase component times the pulse shape and the carrier, as well as the amplitude of the sine component. That is why we have an S GT and sine 2 pi f ct. You might recall a similarity with the expression of the low pass equivalent form that we had arrived initially. So, there we also had x cos 2 pi f ct minus y sin 2 pi f ct. If we see the pulse, if we see the phase shift keying, the x and y are related by their phase. That means we have a single parameter by which we can control. But here we are saying that we choose x and y independently, and then we can get a phase out of it. That is okay. So, we are getting independent phases, so independent amplitudes, while we are modulating this thing. Effectively, we should write as m of t as real part of a m c plus j a m s. So, this is x plus j y according to what we had discussed before, g t e to the power of j 2 pi f c t, and this would result in this expression. And we could also write this as real part of some V m e to the power of j theta m, where V m is square root of a m c squared plus a m s squared, and theta m is the tan inverse of this over this. so times gt e to the power of j 2 pi f c t. You could also write this as real part of Vm gt e to the power of j 2 pi f c t plus theta m. So now you can see that from this particular expression there is an amplitude and here there is a phase. So what we can get from this expression is that the amplitude Vm could be selected independent of the phase and vice versa. This could be one view of this. The other view could be that I have quadrature carriers and I could select phases independently. And of course, to complete this set of expressions, Vm is equal to square root of amc squared plus ams squared, and theta m is equal to tan inverse ams upon amc. So if I would choose amc and ams, I get Vm and theta m, or if I choose Vm and theta m, I get amc and ams in either way. So whatever it is, in the amplitude, in the pulse amplitude modulation, you had only one signal to choose from. That means you would choose the amplitude only, and there was only a cosine, so that was the basis function. In case of phase shift keying, again you had only one parameter to select, that is the phase, and you chose from a whole set of phases available one of the phases, right. That did result in generation of different amplitudes in the I and the cosine, but they were constrained by the phase. Whereas here in this case you have two things to select, that means amplitude and phase, or two different amplitudes. So these are the two different views of quadrature amplitude modulation that is usually available. So we will take one of the views first and then we will look at the other view after a while. So we can think of the quadrature amplitude modulation as M1 level pulse amplitude modulation, that is here, as well as you have M2 level of phase shift keying. So I could give M1 level amplitudes, I could combine M2 level phases. So as an example, suppose I have M1 equals to 2, and if I have M2 equals to 4, let M2 equals to 4. So that means I have two amplitudes, right, and I have four different phases. So if we try to draw our signal space diagram, so I have two different amplitudes. So if I select a D and a minus D, we are actually taking phase and amplitude together. So it's not so easy to plot it directly based on this two phase. So what we do is, let us suppose we have one amplitude level covering a radius as the amplitude. So going by this, there is a certain radius, right, Vm, and there is another amplitude which covers another radius, right. And now we have four phases. So we have discussed four possible phases. So we can mark these as four possible phases, as well as the second amplitude could also have these four phases. Another alternative, rather different option could be that you have this as one amplitude this is another amplitude. These are the 4 different phases of the first amplitude, and these are 4 different phases of the second amplitude, right. So, that means our constellation points. So, we have probably used a new keyword at this point, constellation points. Constellation points would mean these locations. So, this could be, let us say, D1, and this could be, let us say, D2, and these are 4 different phases, these are 4 different phases. So, overall we have 8 different possibilities. So, when we multiply these two, we have a total of M1, M2 constellation, M1, M2 points in the constellation, right, and the number of bits that it can represent would be log base 2 M1 M2, and this would be our choice of k. And then you could easily separate it out as k is equal to log base 2 of M1 plus log base 2 of M2, and that you could say is probably k1 plus k2, right. So, what we are trying to do over here is that you could probably imagine that k1 bits. So, here if it is 8, so there would be 3 bits involved in this. So, out of 3 bits, 1 bit could be used in selecting the amplitude. So, I have 3 bits because there are 8 possible values. So, 8 possible values would be chosen by 3 bits. So, I have 3 bit locations, and so k is equal to 3 in this particular example, and there I am seeing that if M1 is equal to 2, k1 equals to 1 and k2 equals to 2. So, that means I would select, using this I would select M1, and using this I would select M2, because there are 2 bits possible, 0 0 0 1 1 0 1 1. So, that means I have 2 different sources. You can think of it in that way, or you can divide it in this fashion, or you can look at it as a combination. And here again you could use gray coding in order to ensure that the nearest neighbors differ at most by 1 bit. So, again that is not a very straightforward and simple job, and you could try to write an algorithm by which you would map these bits to constellation points or to the signal locations, which would generate the mapping in a gray coding format. All right. So, this is one way of looking at it, and now we move forward and try to look at the signal, the way we write it in terms of a vector notation. So, we could write SMT as SM1 F1T, because clearly it is not one dimensional, it is 2 dimensional. There is an I and there is a Q. So, since it is 2 dimensional, I have 2 basis signals, which I would mark by F1 and F2, and I could write F1 similar to the case of PSK as square root over 2 by EG GT cos 2 pi FCT, and F2T is root over 2 upon EG GT sin 2 pi FCT, and SM could be written as SM1 SM2 in the vector notation, where SM1 would be the amplitude of the cosine components along with EG by 2, so that it normalizes, and AMS with root over EG by 2. So, this way it could be the vector representation, and this is the signal representation. So, what we have done here effectively combined pulse amplitude modulation along with phase shift keying to generate quadrature amplitude modulation, and this way we have generated a new modulation scheme where you have a lot more flexibility. So, in a similar fashion as we have done before, you could calculate the Euclidean distance between 2 points as the norm of Sm minus Sn. Sm is given, Sn would be Sans, and you can keep on doing that, and the end result you are going to get would be d, and the minimum distance, sorry, this would be equal to square root of half Eg AMC minus ANC squared, as we did before, plus AM sine minus AN sine squared, and the d minimum, that means the nearest constellation point, will be given by d 2 root Eg. Along with these kinds of constellations, there is another important constellation way of representing the constellation, which is the sometimes called the square or generally the rectangular constellation. This is an outcome of seeing the signal as amplitude modulation on two quadrature carriers, whereas the one that we have represented here is a combination of PAM and PSK. Appears, I mean, they ultimately are the same, but the visualization could be different. And here what we generally do is, suppose this is my I axis and let this be my q axis. So here we can think of PAM. See, this is pulse amplitude modulation. If you see this carefully, this one is a pulse amplitude modulated signal, this is another pulse amplitude modulated signal, right. So we can think of a pulse amplitude modulated on the I axis, a pulse amplitude modulated on the q axis. So if you are doing pulse amplitude on the I axis, you have a d, you have a minus d, you have a 3d, you have a minus 3d if you have 4 levels, and similarly you can have 4 levels on the q. So what we have done is we have combined a 4 level PAM in the I axis to a 4 level PAM on the q axis, right. So that means we have in the I axis and a 4 level PAM in the q axis. So this would mean that k equals to 2 in the I axis, this would mean k equals to 2 in the q axis. So that means we have 2 bits and we will choose these 4 levels, we have 2 bits, we will choose these 4 levels. So when we combine them, what do we get? When I have, so together we have 4 bits, 2 from the I selection, 2 from the q selection. So that means we have 4 bits, so that means k is equal to 4 combined k, which implies m is equal to 2 to the power of 4, that is 16, right. So let us see whether we get it or not. So when I select 2 bits on the I axis, let us say I have come to this d, I also have to select 2 bits on the q axis. So I could select all of these points, and then a combination of d and d would be a point here. Similarly, I will get a combination there, I will get a combination there, I will get a combination there. So we are able to select all these possible points. So when my I is 3D, I will again get these 4 possible points. When my I is minus 3D, again I am going to get all these possible points. There is a point here. So with these circled plus are all possible constellation points that get generated if we think in terms of the PAM signal. So if we count the total number of such constellation points, it matches our number of 16. So what we see is that this quadrature amplitude modulation can be created, or the constellation for quadrature amplitude modulation can be created in two possible ways. One is where you select a PAM and you mix it with a phase shift keying, and the other is you could do a mixing of two PAMs on separate I and Q axis. So, if we look at this, select a subset here, this is a phase shift keying with one level of amplitude. So, there are 4 possibilities, that means 2 bits, well done. And if I select these, we have 1, 2, 3, 4, 5, 6, 7, 8. So, we have 8 possibilities, so 3 bits. So, now if I would select, let us say, these are the 4, along with this I could select, let us say, these, I could combine this as PAM with PSK as different phases and different amplitudes, but of course, the combination would not be as straightforward as we had drawn the diagram where we had 2 concentric circles and different phases. So, here the representation was easier compared to if we represent over here. So, in both the cases we have 8 possible 1, 2, 3, 4, 5, 6, 7, 8 possible constellations, here also 8 possible constellations, but the way we do the mapping is different. In both the cases with this different color, we could represent with 3 bits, and they would only the constellation shape would be different, and you could even form a PAM on I and PAM on Q, and you could still do a constellation which looks like this. It will be a bit more complicated, but end of the day you are choosing 8 constellation points using these combinations, right? Both the things are valid. Now, what remains is which particular constellation you should choose. We will continue on this discussion in the next lecture. Thank you.